Alright, so here's this week's homework. It's our pink homework. It's due March 22nd. It has Unit 7, Lessons 3 and 4, which are all exponent rules. So Lesson 3 was when we did our power raised to a power rules. It's a little blurry. There we go. It's better. So first, 10 to the 7th squared. Remember, when we have a power raised to a power, that means we multiply the exponents. So this is just 7 times 2, so this would be 10 to the 14th. Next one here, 9 and 3 are exponents. So 9 times 3 would be 10 to the 27th. 6 times 3 would be 10 to the 18th. 2 times 3, 10 to the 6th. 3 times 2, same as 2 times 3, that's also 10 to the 6th. And the last one, 5 times 7 would be 10 to the 35th. Alright, next problem says you have 1 million number cubes, each measuring 1 inch on a side. If you stack the cubes on top of one another to make an enormous tower, how high would they reach? So we have 1 million cubes, stacking them on top of each other. So that would just be 1 million inches high. So we could say, 1 million inches. Let's see, it looks like they've also divided by 12, so they've also turned it into feet. Does it say in feet? No, but if we were to do 1 million divided by 12, that would be 83,333 feet tall. We could even turn that into miles. There's 5,280 feet in a mile, so that would be 15.78 miles as well. Alright, so there's 3 different ways to write that one. It says if you arrange the cubes on the floor to make a square, would the square fit in your classroom? What would its dimensions be? Explain your reasoning. So the square would be, I'll go ahead and draw it here. It'd be 1,000 inches here, 1,000 inches here, because 1,000 by 1,000 times 1,000 would be a million. 1,000 inches, if we divide that by 12 inches per foot, it'd be about 83 feet. So that is a no. Our classroom is not 83 feet long or 83 feet wide. No. One more part to this question. It says if you layered the cubes to make one big cube, what would the dimensions be of the big cube? So now if we're talking about a cube, that means we're going to do it times itself 3 times. So 100 times 100 times 100 would make the 1 million. So if we have a cube, right, all these sides are going to be 100 inches to make a cube with a volume of 1 million. So for that, the volume would be 1 million cubic inches if every side had a side length of 100 inches. Alright, next problem says an amoeba divides to form 2 amoebas after 1 hour. 1 hour later, each of the 2 amoebas divides to form 2 more. Every hour, each amoeba divides to form 2 more. So it says how many amoebas are there after 1 hour? So it starts off with 1. An hour later, there's 2. So it already kind of told us that answer. There's 2. So after 2 hours, right, there's twice that many. It's squared again. So that would be 4 after 2 hours. So this is another way we could write this, I guess, is like 2 to the first, 2 to the second. So now if we're doing after 6 hours, that would be 2 to the sixth. If you went through and solved that, that would be 64. So after 24 hours, now we're getting pretty big. That's 2 to the 24th. If you've got a calculator at home, if you're doing that at home, that would be 16,777,216. It says, why don't my exponential notation be preferable to answer these questions? It would be much faster than writing out the whole number. Alright, we got one more problem on this lesson's homework. It says this goes, oh, that one went back to the first lesson. Let's see. Elena noticed that 9 years ago her cousin Katie was twice as old as Elena was then. Then Elena said, in 4 years I'll be as old as Katie is now. If Elena is currently E years old and Katie is K years old, which system of equations matches this story? So we want to look at each one of these and figure out which one matches up with what's going on. So Elena, let's see, 9 years ago her cousin Katie was twice as old. So we subtract, what, 9 from Elena? In 4 years I'll be as old as Katie is now. So Elena's age plus 4 would be equal to K. So I need to have this for sure. Not this. It's not Katie plus 4 years equals Elena's age. Elena's actually a little bit younger, so we need to have Elena plus 4. So that one's not right. This one could possibly be right. This one could not be right. I think this part right here, in 4 years I'll be as old as Katie is now, is pretty easy to see. That's E plus 4 equals K. The second part is a little more confusing. Elena noticed that 9 years ago her cousin Katie was twice as old as Elena was then. So 9 years ago, we just take 9 off of Elena's age. Her cousin Katie was twice as old as Elena was then. So that would be this one here as well. Alright, so that makes A not true and D our best answer. Alright, so there's lesson 3. We also need to do lesson 4. So here's the back side. Now we have some exponents. We're just going to evaluate what that would be. So hopefully you remember anything to the 0 power is 1. I'm going to zoom in a little bit and see if that helps. If you think zooming in here makes it a little bit easier, maybe let me know and I'll try to have it zoomed in more next week. 10 to the third divided by 10 to the third. Whoops, that's not going to be. Alright. 10 to the third divided by anything divided by itself, right? We should hopefully remember is 1. Now we're adding these together, not multiplying, so we don't have a rule when we're adding the expressions together. But 10 squared is 100, 10 to the first is 10, and 10 to the 0 is 1. So that would be 111. Alright, 100 plus 10 is 110, plus 1 more would be 111. So it says write each expression as a single power of 10. So let's go ahead and start simplifying these. So 10 to the third times 10 to the 7th on top. When we multiply the terms, we add the exponents. So that's 10 to the 7th over 10 to the 5th. Now division rule, we subtract the exponents. So 7 minus 5 would be 10 squared. So that's a single power of 10. We wouldn't change it to 100. We want it with a single exponent here, single power of 10. Now 10 to the 4th times 10 to the 12th over 10 to the 7th. So another way we could write that is 10 to the 4th over 1. So this is a numerator, this is a numerator. We're multiplying those together, we add the exponents. 4 and 12 makes 10 to the 16th. 1 times 10 to the 7th is just 10 to the 7th. Now the division rule, so we have to subtract the exponents. So we have 10 to the 9th Next one here, power rule. So we have to multiply the exponents times the power that it's raised to. That's from lesson 3. So 5 times 4 would be 10 to the 20th on top, and then 3 times 4 would be 10 to the 12th on bottom. Now we can subtract. 20 minus 12 is 10 to the 8th. Alright, next one here, multiplication rule. That means we add the exponents, so 5 and 4 and 6. 4 plus 5 plus 6 is 15, so 10 to the 15th over 3 plus 7 is 10 to the 10th. And now we have division rule, so now we need to subtract the exponents. So that's 10 to the 5th. Alright, last one we have power rule. On both top and bottom, we'll have the division rule. So 5 times 2, so let me slide that up some. 5 times 2, that'd be 10 to the 10th, over 2 times 3, 10 to the 6th. So that'd be 10 to the 4th. Alright, let's see. So going through there, we have 10 squared, 10 to the 9th, 10 to the 8th, 10 to the 5th, and 10 to the 4th. Let's see, next up, number 3. It says the sun is roughly 10 squared times as wide as the Earth. The star KW Sagittarius is roughly 10 to the 5th times as wide as the Earth. But how many times as wide as the sun is KW Sagittarius? Explain how you know. Let's see. So what do we need to do here? That's a division. We need to divide the 10 to the 5th times the 10 squared. 10 to the 5th divided by the 10 squared. So when we have division of the exponents here, we're going to subtract. 5 minus 2 is going to be 10 to the 3rd. Alright, next problem here. I need to move this a little bit. It says bananas cost $1.50 per pound. Quick cameo. Miss Jennings! Alright, bananas cost $1.50 per pound. Guavas cost $3 per pound. Kieran spends $12 on fruit for the breakfast his family is hosting. It says let B be the number of pounds of bananas Kieran buys, and G be the number of pounds of guavas he buys. So writing an equation relating the two variables, rearrange the equation so B is the independent variable, and then rearrange the equation so G is the independent variable. Alright, so what we've got, $1.50 for bananas, $3 for guavas, $12 all together. So B is for bananas, that's obvious. G is for guavas, that's pretty obvious as well. All right, so $1.50, let's see, 1.5 times the number of bananas. All right, $1.50 per pound times the number of pounds, plus $3 times the number of pounds of guavas is going to add up to our $12. So that's a pretty easy equation. Rearrange the equation so B is the independent variable. So now we want to solve for G if B is independent. That means our dependent is going to be equal to the rest of it. So we're solving for G first. So I would do 12. I would subtract the 1.5B to start getting G all by itself. So 12 minus the 1.5B. And then if I want it equal to G, I would also need to divide by that 3. Okay, it might be a little better to actually work this out over here to the right. 1.5B plus 3G equals 12. So I subtract the 1.5B from both sides. So I have 3G equals 12 minus 1.5B. Then I need to divide by 3 here to solve for just G. So G equals 12 minus 1.5B, all divided by 3. We could leave it that way, or we could divide this and this by the 3. That would be g equals 4 minus 1.5 over 3 would be 1/2. Or you could write it as 0.5b. Okay, so here's one way to answer for part B. Now we're going to rearrange for G, so we're doing the exact same thing, except now we're going to solve for B. Alright, so for part C, let's start with that same equation again, 1.5b plus 3g equals 12. This time we want to solve for B, so let's get the 3g away. Let's get it over here. So 1.5b equals 12 minus 3g, and then divide everything by 1.5. So b is equal to 12 divided by 1.5 would be 8, and then 3 divided by the 1.5 would be 2. Alright, so here's our answer for part C right here. Alright, one more question, and it's a throwback all the way to Unit 3. It says Lynn's mom bikes at a constant speed of 12 miles per hour. Lynn walks at a constant speed of 1/3 of the speed her mom bikes. Sketch a graph of both of these relationships. So it doesn't say anything about a starting spot. We just know the speeds. So it looks like Lynn's mom is going 12, which doesn't actually look like it's going to be on here, right? 2, 4, 6, 8, it only goes up to 10. So we're going to get 12 miles per hour. I guess we could do 0.5 hours and do 6 miles. So that would be like Lynn's mom right there. Let me get something straight here to graph that for Lynn's mom. Maybe got a little crooked at the end there. So here we have Lynn's mom, her graph. Lynn walks at a constant speed 1/3 of that speed. So however far she was going at any certain point here, we could divide that by 3, right, or multiply it by 1/3. So instead of going 6 miles in half an hour, she could only go 2 miles in half an hour, right? Because 6 divided by 3 would be 2. Alright, so I think that's probably the easiest way to graph this one, is just to do this half hour. Alright, so here's Lynn, and there's Lynn's mom. Alright, so I'll take care of this week's homework. 18 minutes, not too bad. Make sure you get this turned in by Friday, please. Thank you.